Our last video focused primarily about kind of older school things in C++. We talked about how template functions improve upon macros. We talked about how for older compilers you can explicitly instantiate the parameters and the types for methods, for member functions, for classes, and so on. Now we're going to zip forward about a decade and a half or so and focus on some newer features in C++ with respect to templates. And the first thing we're going to talk about here is the concept of variadic templates, which allow you to be able to write code that can have variable numbers of parameters and have the compiler manage this through the variadic template mechanism in a type-safe and highly efficient way. So to do this, we're going to take a look at a little function called adder. And we've got two versions of this adder function. It's basically an overloaded function. And the first one is this version, which is parameterized by type name t. And it takes a single instance of t, and it goes ahead and returns it. So this is going to be the base case for our recursive adder variadic template magic we're about to look at. We're also going to use a little macro called pretty function, which is going to demonstrate the name of the function that's called along with the parameters. And this will help us see what's actually going on here in the code. Okay, so, and I think what I'm going to do here is say, let me go ahead and put this in parens, so we'll be able to differentiate this call from the other call. So let's do it like that. All right, so then here's the other overloaded version of adder, and this has some pretty interesting syntax in it. This has what's called variadic template parameters. And the way we define that is you can say template type name t, like we did before up here, and then we can also say type name ... and then we say args. And what that's basically saying is this is a variable number of template parameters. And if you provide a variable number of calls, a variable number of parameters to the adder function, this variadic feature will handle them all in a very efficient and type-safe manner. So let's take a look at how this gets played out in practice. You can see the first parameter to adder is the first element. And then the second parameter that's passed in is one of these variadic template arguments. So it's args ... args, where first args is a capital A. Again, we have our little pretty function here to print out what's happening. And then here's where the magic starts. We say first plus adder, and then we pass in all the args that are defined here. Now at this point, this function definition doesn't know how many parameters are actually going to be passed to it. It's going to let the compiler template mechanism figure this out. So let's go ahead and take a look at a couple of examples that will demonstrate how the compiler template mechanism will figure this out. So here's the main program, and this program basically will demonstrate the use of variadic template functions. And you can see here, the first thing we're going to do is we're going to define ourselves a sum, an auto sum, which is going to be the sum of calling the adder variadic template function with a variable number of arguments. So 1, 2, 3, 4, 1, 2, 3, 8, 7, 10, 21. And you'll notice that I can tack on new parameters here willy-nilly, and let's put 4 in there. We put 4 before. And that's okay. When this code gets compiled, magic will happen, and it'll handle the variable number of parameters that are passed to it in a nice, efficient, type-safe way. Well, I don't need quite all these parameters, so let's go ahead and remove a few of them. So let's end up with, here we'll have 6 parameters just for kicks. So that, as you can imagine, is going to sum the results of these things, and we'll see in a minute how that actually works under the hood. The second thing I'm going to show you is we're going to do the same thing, except this time we're going to do it for strings, not for the ints we have up above. So I'm going to define 5 strings, C++ space is space cool. So strings S1 through S5. And then I'm going to go ahead and use adder again, and I'm going to give a variable number of parameters here. And of course, I could keep adding more strings if I wanted to. The point is that it doesn't matter how many things I add, the compiler will figure it out at compile time and then do some magic to make it all work together. Now, in this case, what's happening is we're using the fact that the plus operation on a string does concatenation. So basically what we're doing is we're summing the results of C++ is cool. Let's go ahead and run this code, and we'll see not only the results, but we'll also see how the results transpired. And so if you take a look here, you can see how the code actually works. So notice when we call this version of adder here, it goes ahead and calls this function there. And you can see that it takes the first element here, which is this guy, followed by all the args. And it goes ahead and says first plus adder args. And what that does is that recursively then calls itself, stripping off one of the elements because we just took one of them off. So the next time it's called, it's got the first plus 4 args, and then the first plus 3 args, and then the first plus 2 args, the first plus 1 args. And then finally, we end up with the base case of the recursion, which is this version here. And as you can see, that's the one I put the little parens around so we could tell that that was the one there that's doing that. So that's the base case of the recursion. And then what's going to happen is it's going to go ahead and add everything together and return the sum of 25. So the nice thing about this is it's very efficient, it's very type safe, and you don't have to know or care how many parameters are actually passed in to adder. We do the same thing down here with the adder version that works with strings. It's a little bit more unwieldy because, as you can see, there's a lot of stuff that's passed with the strings, so the pretty function gets more complicated, but it's basically the same idea. And the end result is we end up with a final string that says C++ is cool. And I think this is a really cool example and demonstrates some very powerful features of C++ and variadic template arguments. There's some other features that you can use with this we've talked about previously in the context of the in-place methods on our stack, or the in-place back methods on sequential containers like vectors and decks and so on. And they use some similar techniques to be able to move or forward variadic parameters in such a way that it's very efficient and there's no unnecessary copying taking place. So super powerful, newer feature in C++. You may find a use for it before the class is done. All right, the next thing I want to do is talk about another newer feature of C++. And this is basically falls into the category of what's known as template metaprogramming. And this is kind of the black art of templates, and it's very cool. So what I'm going to do here is I'm going to define, just the taking on faith, the factorial of 20. So just take it on faith that that's the factorial of 20. It is, but I'll prove it to you in a minute. And then we're going to show various ways of computing the factorial of 20, which, as you can see, is a very large number. In fact, it's so big, it has to be stored as a long. Long wasn't big enough. We have to do a long. So this is a const long, and that's the value. So let's take a look at a couple different ways to compute the factorial of 20. The first approach is something you probably have seen before in an algorithms class or data structures class, or maybe even CS 101 style class, where you compute factorial recursively. So here's a function called factorial where you pass in the value you want to be computed, like factorial of 20. And we start out with a default parameter, which is the sum of 1. So we start at 1. And if the value of the val parameter is greater than 1, then we call ourselves recursively subtracting 1 from val, and then taking the current value of val and multiplying it by the current value of sum. So you can see what's going to happen here is this, as this thing calls itself down, it's going to go ahead, let's say we call it with factorial of 20, then it's going to go ahead and call itself factorial of 19, and then sum times val, and then it's going to go ahead and it's going to call it with factorial of 18, and then that's going to be sum times val. And so each time we call this thing, it's going to basically grow and shrink and come together to compute the n factorial. When it's equal, when the value of val is basically 1, we just return sum, which would be whatever the sum is at that point. Okay, so that's the classic recursive way of defining a factorial that's computed at runtime. Well, let's now go ahead and take a look at some other cool features that are built into C++ that allows you to compute these values at compile time. Now, the first version we're going to look at doesn't really have anything to do with templates, but the second version will. So the first version we're going to look at here is something called a const expr function. And so I named this C factorial for const. C is for const. And at first blush, it looks pretty much identical to the factorial I wrote above. The difference is the factorial above is computed at runtime when the program is running, whereas the C factorial that's noted as a const expr is computed at compile time. So the compiler basically does the computation of this function as it's doing the compilation itself, and will end up with a single result, whatever you asked it to be the factorial of. So again, the code is identical, but it's all computed at compile time. How can we prove to ourselves it's computed at compile time? Well, here's what we're going to do. We're going to define ourselves an enum with an enumeration literal compile time generated value, and we're going to assign it whatever comes back from C factorial of 20. And the thing to remember about enums is they have to be given a value at compile time. You can't give an enum a value at runtime. It has to be at compile time. It's basically a constant. And so therefore that demonstrates that C factorial is in fact a constant value that's returned at the compiler by the compiler at compile time. And just to go one step further, there's actually an assert mechanism built into C++ that will cause the compiler to print an error message if the value that's compared in the assertion happens to fail. So if compile time generated value doesn't equal factorial of 20, which is this constant we defined up here, then this code will cause the compiler to stop and give you an error. Well, it may not stop, but it'll give you an error as it's compiling. All right, so that's one way of being able to compute values at compile time. Let's now go ahead and take a look at a more interesting way that uses C++ template metaprogramming in order to do this. And this is going to define a compile time factorial template using a generic meta function that calls itself by inheriting from itself. This is completely insane, by the way. So, but it's also really cool. So here's the template. We're going to have two parameters to the template, much like we had two parameters to the C factorial const expr. But if you take a look, this version is going to have the first parameter be a long, which is the initial value we're trying to compute the factorial of, and the second value is going to be the sum, and it's going to default to 1. Again, very much like this function up here. Now, the difference here between the function and the template is this is templates. If you recall, we talked the other day about how templates can have non-type parameters, and this is a classic example of that. So this template takes two non-type parameters, a long, and a sum. And then it defines the template itself recursively in terms of the template parameters that are passed to it. And so struct factorial is defined as inheriting from struct factorial of LLN minus 1, and then LLN times LSum. So again, that's pretty much exactly the same logic we saw up here in this function, except now it's being done when we're defining the template itself. Now, just like with the adder variadic argument template we looked at in the previous example, we need to have a basis case for our recursion, so this thing won't just keep compiling forever. And here it is. This is a specialized meta function that has a value and does not inherit from itself. So you can see here that what we do is we define factorial of 1 to be whatever LSum is at this point. And then we're going to define value to be what LSum is when all is said and done. So this is a specialized version of the factorial struct that's going to define the enum. So now let's go ahead and see how we can actually use this. So what we do is we say, compiler, please compute for me the factorial of 20. So you can see factorial of 20, that goes into here, default value of 1, value of 20, and that starts the process of doing the template metaprogramming reduction. And it's going to keep doing this until it finally gets to the point where ln minus 1 equals 1. And of course, ln times LSum will then be the factorial. And so that value is then stored here in a const long called fac. And just to make sure it's working properly, once again, we use our good friend, the static assert, and we say, hey, is fact here really equal to the factorial of 20 that we defined up there? And of course, the answer had better be yes. And if it's not yes, then the compiler will throw up an error and complain at you. The last thing I want to do with this example is just demonstrate how we can also do dynamic runtime assertions. So this is actually code that gets run in the main program. And here we use the runtime recursive version of factorial to compute the factorial of 20 and just make sure that it actually equals the constant we defined earlier. And then we print the results out. So let's go ahead and run this code. You can see that it does in fact compute the right result. And just to demonstrate how static asserts work, if I was to go up here and change the factorial of 20's value, which of course is incorrect, but just to change it, just to cause everything to throw up, let's go ahead and recompile this. And you can see now that we get a static assert failed here because, of course, the value that was generated by C factorial is no longer equal to the factorial of 20 const. That was incorrect. And likewise, you can see down here, the factorial we computed from using the template metaprogramming version of the factorial struct also no longer equals that const. So these are getting us compile time errors, which is exactly what we want. Let me go back and rechange this code before I forget so that future versions of this lesson don't start out wrong. Okay, so that was a walkthrough of some more modern features of C++ templates, variadic template arguments, and the ability to do template metaprogramming, as well as also giving you a chance to learn a bit about const experts. So hopefully you found this useful. We'll obviously continue our discussions about other features and facets of C++ templates and other aspects of STL here very shortly.